So in this little section here, I'm going to basically just illustrate the argument for why limits are unique when they exist. So, I mean, just to kind of explain what this means, okay? I mean, uniqueness is a term that we use in math a lot. And all it means is that we say an object is unique when there are no other objects which have the same properties as it. So for instance, a number, which is the limit of a sequence, would be unique as the limit of that sequence if there's no other number which is also a limit of the sequence. Okay, now it might seem like obvious that a sequence couldn't have two different limits, but again, this is one of those things that we have to deal with. I mean, we have to just show rigorously given our definition, right? Like we made a definition and we want to use that definition very carefully. And if we're going to do that, we want to show that it has all the properties that we hope it would have, right? And uniqueness is one of them. So let's, so basically I'm just going to, okay, well, let's imagine. The proof they give in the book proceeds by contradiction. So they basically assume that something, they assume that a sequence has a non-unique limit. So they assume that there's some sequence with two different limits. So, and then they show that that's kind of impossible, right? That's how contradiction works. So let's imagine Sn is a sequence such that Sn converges to a number S and Sn converges to a number T where S is not equal to T, right? So the key here would be to basically try to use the definition of convergence to show that this doesn't make any sense, okay? And instead of actually going through the argument symbolically in detail the way they do it in the book, I'm just going to show you a picture of why this is totally impossible. So let's sort of imagine plotting our sequence here. I'm just going to sort of pretend, for the sake of making this picture simpler, that the sequence is just all positive, but obviously you could draw a similarly good picture for a sequence where some of the values were negative. It doesn't matter. So let's, well, first let's plot the values of S and T. So let's just pretend that they're both positive, and let's pretend that S is smaller than T. So here's S. And then here's T. Okay. And then it doesn't really, we don't know where the values of the sequence are. Maybe there's some, like that, who knows, initially at least. But then obviously the idea is that as you go further and further, they need to converge to these two different numbers, right? So what we need to do is we're assuming, okay, and I'm going to talk more about this in a later section where we talk about proofs with convergence, but it's a little bit different here. Like normally before, I was talking about how to prove that a sequence does converge, okay? The way you use the definition becomes different when you're assuming that a sequence does converge to a number. Then if you want to leverage that assumption, you sort of have a different type of control over the variables. So here, what we can do is we can say, because we assume that Sn converges to S and that Sn converges to T, we can pick whatever number epsilon we want. And then that assumption of convergence guarantees that some number capital N will exist for, according to the definition of convergence for S, and another number will exist for the definition of T. But the key here is that we can pick a value of epsilon at the beginning, okay? So let's imagine basically picking epsilon so that, because basically, right, the idea is that if we pick epsilon, that'll make two bands. So like, let's say this is t minus epsilon, and then this is t plus epsilon, right? Sorry, the handwriting's a little bit bad. So this is t minus epsilon, this is t plus epsilon. By picking that epsilon, there has to be a capital N, which basically makes the sequence stay within this band around t after that value of capital N, right? So here's this. Actually, better yet, let me kind of do these in a different color maybe to make it really clear. So, oops. Doesn't really matter. Let's say, I don't know, red. So here we have a, actually, is there a dotted line? I don't see a dotted line. All right. So here we have one band, right? So I'm going to kind of fill it in like that. Actually, it doesn't look very good. All right, whatever. You guys can see it. And then let's say we have another band of the same width. Oops. Around S. Okay. So here we have S minus epsilon, S plus epsilon, and then we'll have another band. I'll just make this one green. Actually, hold on. I think I saw a, what if I do this? Oh, hey, what do you know? All right, nice. So that looks pretty good. Okay, so we have this red band and we have a green band. Still learning here. So basically, right, okay, we picked some number epsilon, and the key was to make epsilon be small enough that these two bands didn't overlap each other, okay? And you'll see why in a second. So basically, when we pick this number epsilon, then the definition of convergence, if we're assuming that Sn converges to T, it guarantees we can find a number capital N. So I'm gonna actually draw, like, let's call it capital, oh, actually, let's focus on S first. So the convergence for S guarantees that we can find some number N1, oops. Let's say it's over here. So let's say N1 is over here. Now beyond this point N1, the sequence has to stay inside of this band. That's because we assumed it converges to S, okay? But there's a similar number for T, right? So let's say it's N2, maybe N2 is over here, right? Then the sequence also has to be in this band. So at this point, beyond both of these two numbers, and I don't know which order the numbers are in, like N2 might be before N1, like might be smaller than N1, but it doesn't really matter. At the point where you've passed both of those numbers over here, the sequence needs to be in both bands at the same time. Yeah, in fact, hold on. So we can just make another one of these cool rectangles. So what if I do it like this? Yeah. So beyond this point, okay, that's kind of weird looking, but whatever. Beyond this point, right, the sequence has to stay within both of these two bands at the same time, but that's impossible because the bands don't overlap each other, right? So that's the basic idea. That's the reason that there cannot be two different limits at the same time. This is literally the argument that the book gives in pictorial form. So with that, I also want to give you guys a lecture question. And what I decided on was this. So I'm just gonna clear everything. And oops, yeah. All right. So let's call this lecture 3, question 1. And this is something that you should submit on the homework. So let's take the sequence Sn to be, let's say, mn plus 1 over 2n squared cosine of n pi over 12. Okay, so first of all, well, okay. Let's just say this. Find find a value of epsilon such that for any proposed limit S, the sequence never stays within distance epsilon of S, okay? So sorry if this wording is a little bit confusing, but basically the idea is, right, if you want to show, I'll tell you off the bat in case it's not clear, that this sequence does not converge to any number, okay? It has no limit. This is a divergent sequence. So the idea is that you can actually pick a number epsilon, right? When you want to show something's divergent, you can like pick epsilon and then say, well, if you have a proposed limit, right? Like if you say, well, let's show it doesn't converge to this number, you can pick some number epsilon and then show that no matter how far out you go, the sequence keeps jumping out of the band of width epsilon, right? It doesn't always stay within epsilon away from your proposed limit. There's actually a single number you can pick here, which would work for all possible limits, right? All false limits here. You can pick a single number epsilon so that no matter what limit you try to pick, no matter how far out you go, you'll always find points that are farther than epsilon away. So take a few minutes to think about that and pause the video. Okay, so now I'll explain this. So basically, in this case, it looks like a complicated expression, but it helps to just try to visualize, like, I mean, even without, like, you don't have to plot it carefully with dots and stuff, just draw kind of a general sketch, like a graph of what shape this looks like it would have, right? So basically here we see this cosine of n pi over 12, it's like something that oscillates, right? Between like plus and minus 1, right? But then this thing out here is sort of this like amplitude, which causes the oscillation to be, you know, wider or smaller depending on how big this is. And if you think about what's happening here, this is actually just a number. This tends towards 1/2 over here, right? And it starts off bigger and then it gets smaller. So you start off with like kind of a bigger amplitude, and then it goes down and down and down, and it approaches 1/2. So basically, the picture you can draw here. So I'm just gonna basically erase all of this stuff, and I'll sketch this sequence for you. So the picture you can draw of this sequence would be something like this. And I'm not even going to do it as dots. I'm just going to do it as a curve, even though it would be like dots in this shape, right? So it looks something like this. Oops. So basically, there's kind of these trend lines like this, or an envelope, if you want to call it that, which approach plus and minus 1/2, right? And so basically the sequence, it's tending, the sort of, the tendency for is for it to oscillate between plus and minus 1/2 as you get further and further out. Now, let's imagine what's the worst limit we could pick that tries to stay as close to all of the sequence, all the values in the sequence as possible. Well, probably 0, right? Because if you try to pick a limit above 0, then there will be points below 0 that are like super far away from that. And if you try to pick a limit below 0, there will be points above 0 that are really far away. So the thing that kind of minimizes the worst case distance is if you pick 0, right? So if we pick 0 as our proposed limit, what value of epsilon would show that 0 is not actually the limit of this sequence? Well, any value of epsilon below whatever the amplitude of this wave would be. In fact, actually, even taking epsilon to be 1/2, I believe should work. But if you want to be safe, you could just pick something smaller, like epsilon equals 1/3. Oops, 1/3, and so on, right? So basically, if you pick epsilon to be 1/2 or smaller, right, then no matter how far out we go in the sequence, right, this is what I'm saying. No matter how far out we go, there will always be points at the tips of these arches, right, which are more than epsilon away from 0. Okay, and the same thing would be true for any other limit. So let's imagine we tried to say that the limit of this was like 1/2 or something, right? Actually, 1/2 is up here. Okay, let's say we tried to say the limit of this was 1/4 or something like that, right? Here's 1/4. We're claiming that the limit is 1/4. Okay, now for this same value of epsilon, right, no matter how far out you go in the sequence, there will always be points on the bottoms of these arches down here, which are more than 1/2 away from this proposed limiting value. Okay, so that's why this value of epsilon is good enough to say that like no limit you attempt to pick will actually be the limit of this sequence. It doesn't converge to any number at all. So I hope that that is clear to you guys. It's hard to explain these things because the logic gets a little bit complicated. So it takes some getting used to. So yeah, anyway, in the next video, I'll talk more about how to prove things using convergence, and we'll actually go through some proofs in detail, and I'll write them out so you'll see what they look like.